Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on the Math Lovers book. I'm starting a new chapter, as a matter of fact, a new section, and I think I should give you a little bit of an overview first. There's 5 sections total in the first 2 volumes of the Math Lovers book. There's 3 in the first volume, which is what I'm on now. I just finished section 1, which is on numbers, and that included 4 chapters. Basically natural numbers, rational numbers, irrational numbers, and complex numbers. So we're done with numbers. Those are usually the first things you learn about when you learn math. Most people seem to think math is mainly about numbers, maybe numbers and shapes if you like geometry. But there's actually something else. And now I'm starting section 2, by the way, and I call that abstract algebra. And so now we're going to get into some more abstract stuff, things you might not be as familiar with as numbers or shapes. And the first of those things is sets, and you probably learned about sets in grade school. I don't think sets even used to be part of a standard grade school curriculum. As far as I understand, I learned about sets when I was a kid, but my understanding is that set theory was part of new math that started in the 1950s after Sputnik, and I heard a lot of people got very confused when they learned about sets. Maybe they were taught it badly. I don't know. Maybe the teachers didn't really understand sets very well. But I think they're pretty basic. And, maybe I should give you a little bit more of an overview. So sets are the most base, I'd say the most basic area of abstract algebra. And you'll see sets aren't very hard. And then after sets, we've got groups. Groups are a lot more complicated than sets, but groups are fun. I don't know if you guys know any group theory. I have a few videos on group theory. I think group theory is great. And group theory is really useful in the sciences. So a group is actually a special type of set with some additional structure. And it's a way to study symmetry. And then after groups, I talk about logic. And you can actually, there's a mathematical theory of logic. And as a matter of fact, math is based on logic. So logic is kind of like the nuts and bolts of math. But I guess, most people, when they learn math, they don't really learn about logic. They just kind of take for granted that they're using it. But logic is all about how to prove things in math. It's how to do math. It's basically everything in math we study is a logical framework, and it involves logic. Those are the rules of math, if you like. So that'll be chapter 7, logic. And then chapter 8 is on computation. That's actually a very useful application of logic. That's how computers work. It's the theory of how computers work. And if we didn't have the theory of computation, which is mainly due to 2 big pioneers, I believe it was von Neumann, he was a Hungarian mathematician, and also Alan Turing, who came up with the idea of Turing machines, which really became the basis for computation. So we owe computers to them, and that'll be everything in section 2. There is a third section of volume 1. That's going to be on chaos, dynamical systems and chaos. That's chapter 9, and then fractals. This is a newer area of math. The kind of mathematical theory of chaos and fractals wasn't really fully developed, I'd say, until the 1960s. So this is probably the newest area of math in my book, but it's not that hard, and I think it's fascinating. And it's there's still a lot of research in this area. So that's just an overview of what's coming up in volume 1, and I'm not going to go over what's in volume 2. That's more academic. That's going to involve things like calculus and probability and statistics, but I'm not going to talk about that right now. Anyway, so let's just delve into chapter 5, which is set theory. And the first section, this is going to be a pretty brief video. I'm just going to talk about what sets are. So what is a set? And naive, there was a thing called naive set theory. When set theory was first invented, I don't know who. I think it was. Most people say that the pioneer of set theory was a German mathematician named Georg Cantor. Actually, people thought they knew what sets were before him. It turned out they didn't. The most naive definition of a set, and this is what's called naive set theory. A set is just a collection of things, a collection of objects. So pretty much any collection can be a set. like the people in your house, the people in your family, the books on your bookshelf, and any collection. It doesn't even have to be a real collection. It could be abstract things, like it could be the numbers 1 through 5. I mean, but that's not quite true. There are some restrictions on sets. That's why I say this was naive set theory, and you will see this by the end of this video. I'll explain some things that aren't sets. Technically, collections of objects are called classes. They're more general than sets. Sets are a little bit more restrictive than that. And it turns out if we don't put these restrictions on sets, you get a lot of paradoxes. You get things like Russell's paradox. And that's why we had to move away from naive set theory. And that's basically what Georg Cantor did. He fixed set theory to make it free of all these paradoxes. Anyway, here's some examples of some sets. The first two sets are finite sets. These are sets with 5 elements. S1, that's just a set of numbers from 1 to 5. 1, 2, 3, 4, 5. A number is a thing. It's an object. And the things inside the set are called elements. So this set has 5 elements. Another way to say that is its cardinal number, or its cardinality, is 5. And S2 is just the same set, it turns out. This is the set where you just write the elements in opposite order. And it doesn't matter the order in which you write the elements of a set. So it turns out S1 and S2 are really the same set, because the order doesn't matter. There are things called ordered sets or tuples where the order does matter. But with these sets that I'm talking about here, the order in which you write the elements inside the set doesn't matter. And sets, like I said, can be finite or infinite. S3 is the set of natural numbers, 1, 2, 3, 4, so on, which a lot of people use the symbol n. I think n is a little bit archaic right now because there's a little bit of an ambiguity about n. It stands for the natural numbers, and I guess in the old days everybody thought natural numbers started with 1, counting numbers, because everybody started counting with 1. Now I think most mathematicians prefer to start counting with 0. So now people are changing their definition of n to include 0. Usually people write z plus, the positive integers, for what used to be called n. But anyway, that's an infinite set, obviously. And then we have another bigger set, even the set of real numbers. And, I'm going to jump the gun a little bit here. Sets, like I said, can be finite or infinite. But it turns out there's different types of infinity. There's actually different sizes of infinity. I'm going to prove this later. It's a pretty shocking result. Cantor proved this. Cantor proved this in the I think around 1880. He proved that there are different sizes of infinity. There's actually different sizes of infinite sets. And it turns out that the smallest infinite set, this was called the Aleph null. That's the symbol we use for the cardinal number of the natural numbers. That's the smallest infinite cardinal number. But then it turns out that the real numbers, there's actually more real numbers than the integers. You can prove this. It's a weird proof, but this has a bigger cardinal number. Usually people call it C, which stands for the continuum. Some people, there is a version of set theory in which C is the next cardinal number after Aleph null, but it turns out that doesn't have to be true. It depends on how you define it. You have to include that as an axiom. I'm really jumping the gun here. I hope I'm not confusing you guys too much. If I have, just suffice it to say that S1 and S2 are finite sets, and they're the same set in disguise. S3 and S4 are infinite sets. And if it bothers you that S4 is bigger than S3, then you can forget that I said that. But and then the elements of sets don't have to be numbers; they can be objects. I mean, S5, I'm writing in the set that contains the elements apple, orange, and banana. And I guess these are just words the way I've written them down. But you could actually have a set where you have an actual apple, and an actual orange, and an actual banana. That's a set of objects. And another peculiar thing about sets is the elements of sets can be sets themselves. So S7, that's probably the most complicated set I've written down here. This actually has 2 elements. S6 has 3 elements, clearly. But S7 only has 2 elements. The first element is an apple. But then the second element is a set. It's a set containing another apple and an orange. So that is actually a set that has one element that's an object and another element that's a set. And that second set, that's called a subset, has two objects in it. Okay, but there's something, there's another example I didn't go over. Actually, I jumped the gun here. S5. This is kind of a peculiar one. This is a set with no elements in it. It turns out there is a set. Sets don't have to have anything in them. And there's only one set that has no elements, and that's called the empty set, or the null set. And I think a lot of people, when they first learn about the empty set or the null set, they're kind of bothered by it because why even bother having a set with no elements? Well, it turns out it's very useful to define such a set, even though it's not a very interesting set. And we actually use a symbol for the empty set or the null set. It's kind of like the Greek letter phi. It's a circle with a diagonal line going through it. That's the symbol for the empty set. And there's one other thing about sets. They can't have repeated elements. For instance, the set 1 comma 1 is not a set because it has two elements that are identical, and that's not allowed. And similarly, if you had a set like water, fire, air, earth, water, that has water in it twice, that's not a set either. And the other thing you can't have with sets is this is actually where counterfeit set theory from naive set theory. You get problems if you allow sets to include themselves. Remember I said sets can include elements that are sets themselves. Well, the only restriction on that is that no set can include itself as an element. If you allow that, you get a lot of paradoxes. So, for instance, the set S that's equal to the S comma T, where S is itself, is not allowed. It's not a set. It is a class, but it's not a set. So that's pretty much what sets are. I mean, pretty intuitive, I'd say. Just collections of objects with a few, restrictions. But most of the time, we don't have to worry about the restrictions. And that's what sets are. And you'll see how useful sets are. I'm gonna do a lot of stuff with sets in future videos. This is just an introduction. So now you know what sets are, and you know what some examples of sets are. So that completes my video for tonight on sets. And thank you for watching, and long live math, and I'll see you guys next time. Bye.